Okay, here's a video on solving exponential equations. I'm going to show you several examples, and I'm just going to try to talk about each of the scenarios that you might run into in this course. For this first one, we've got like bases. So you see how both sides of this equation have a base of 4. Well, with a common base, it makes it just kind of where you focus on the exponents. So notice here, if 4 to the 2p is equal to 4 to the negative 2p minus 1, the exponents are going to have to be equal in order for these two things to be equal because of the like bases. So I actually can jump straight to, again, because the bases are the same, to setting the exponents equal to each other and then just solving for p. Again, my goal is to get p by itself, and 4 to the 2p should be equal to 4 to the negative 2p minus 1. Therefore, in order for that to happen, the exponents had to be equal. So we're going to solve this, add 2p to both sides, trying to get all the p's on the same side. That's 4p is negative 1. And then now I'm just going to divide everything by 4, and p is equal to negative 1/4. So that's how I would do a like base exponential equation. Okay, let's move over to something that looks like this. Now, that's not like bases, so you're like, oh, that's not going to be as quickly solved. But if you actually think about 1 as 4 to the 0 power, then you actually will get back to like bases. So you might run into some numbers where you can rewrite them as the same base as the opposite side to a certain power. So this is one of those scenarios here. So if I go ahead and rewrite 4 to the 3x minus 2 is equal to 4 to the 0 power, now I do have those common bases, and I could set the exponents equal. 3x minus 2 is equal to 0. Add 2 to both sides in an effort to get x by itself. 3x is equal to 2. Divide everything by 3, and x is equal to 2/3. Then I can get to something that involves some of our exponential properties, and keeping in mind that I might need to condense into one base and one set of exponents before I start solving. So remember, I'm multiplying like bases. That means I can add the exponents. So this would be the exact same thing. So I start with that, and then now I've got like bases, and I want to set their exponents equal to each other. And interesting enough here, everything's an m, so that kind of lends itself to thinking maybe I could have something interesting happen, but let's just continue to solve. So 3m minus m makes it 2m equals negative 2m. I'll add 2m to both sides so that I can get all the m's on the same side. And when I add 2m over here, I'm left with just 0. So divide both sides by 4 in an effort to get m by itself. M is equal to 0. And 0 is okay. 0 is a number. 0 is fine. If you plug a 0 in, I would get the same thing on the left as I do on the right. 0 is okay. 0 does not mean you did anything wrong. Now I've got a scenario where I don't have like bases, and I don't have the ability to rewrite 17 as 3 to some power. So now what I'm going to do is use some logarithms. Logarithms are the inverse of exponentials, and they help us get exponents out of the air and down onto the ground with everything else so that our algebra makes a little bit more sense. So first things first, in an effort to undo exponentials, I'm going to take the log of both sides. So log of 3 to the b equals log of 17. Remember, if I don't have a base here, that's log base 10, and log base 10 is in my calculator, so I feel really good about that, and eventually I'll get to use my calculator for this problem. Don't forget that we have some exponential and logarithmic properties. Here I'm going to use some log properties to help me get this exponent out of the air and onto the ground. Keep in mind that that exponent means the same thing as multiplying by the exponent. Nothing changed on my right side. So b times log 3 equals log 17. And again, my goal is to get b by itself. So b jammed up next to log means multiply. So I unmultiply by dividing. Almost messed that up. Here we go. Let's divide both sides by the log of 3 because I'm trying to get b by itself. Those cancel. B is equal to log of 17 divided by log of 3. So I just grab my calculator and type in log 17 divided by log 3, and I'll get the number for that. Okay, so log of 17 divided by log of 3, I get 2.58. So B is 2.58. So if you kind of trace your steps back to the beginning, you're asking yourself, what do I raise 3 to get 17? Well, 3 to the 2.58 power is 17. And if you go to type that back in your calculator to check your answer, you're going to be slightly off of 17 because I did have to round. But that's okay. You can see where this is coming from. I'm looking for the power that I raised 3 to get 17. All right, let's try another example with a little bit more complexity to it, but I think we could still handle it. Keeping in mind that I want to get those ends out of the air and onto the ground, so I am going to use some logs eventually. But before I start doing that, I know it's easy to focus on the exponents, but before I do that, I need to isolate that. So I'm going to go ahead and subtract 3 first. This is the reverse order of operations while I'm solving. So 9 to the n plus 10 power is equal to 78. And now I'm ready to start taking the log of both sides. So that's going to be log of 9 to the n plus 10 is equal to log of 78. And now that n plus 10 becomes a coefficient. Log of 9 equals log of 78. And again, I feel really good about log base 10 because that's in my calculator. This is being multiplied by this. So how do I unmultiply? I divide. So trying to get n by itself, I'm going to divide both sides by the log of 9. That way these guys cancel out. I'm left with n plus 10 is equal to, and I could go to my calculator now, so log of 78 divided by log of 9. Hit enter, 1.98. And now last step to get n by itself, subtract 10 from both sides. And n is equal to 1.98 minus 10, or negative 8.02. And that is how I solve that exponential equation.